All right, I'm recording now, but we just did review so far of what we talked about last time. So, okay. So yeah, we have a Hilbert space. We have operators on the Hilbert space. We define our Hermitian conjugate of an operator, and we had these two special operators, Hermitian, where A is equal to A dagger, or if you want to be a little bit more specific, it's for any two vectors. The action of this A dagger is, of course, defined as this from above, but we're just saying that that's also equal to just the regular action of A. And this is the true sense in which an operator's Hermitian is in terms of this inner product statement. And the reason there's a subtlety between this statement, which is called self-adjointness, and this one is sometimes A doesn't act on all vectors in the Hilbert space. A is only defined on some domain, which is denoted by D of A. This is a set of vectors on which A acts. It's a domain. So there's some set of vectors on which A is properly defined. And that'll come up when we're talking about infinite dimensional things. But I mention that now just so that later on, when I introduce it, you'll remember, oh yeah, we saw that at some point, or we mentioned it. Okay, and the other one is a unitary matrix, and that's one in which the A dagger is the inverse of A. That when you multiply A dagger by A, you just get the inverse of A. And for finite dimensions, so this is called like a left inverse, because you take A and you multiply it with something on the left and you get the identity. So the inverse is on the left of the operator. And for finite dimensions, the left inverse is the same as the right inverse. So this is also equal to A dagger. And I think for the most part, that's always going to be true. This is, by the way, called a right inverse, right? Because now it's on the right of A, and it's acting as the inverse. And for us, that'll always be the case. But in principle, just because they have a left inverse doesn't mean that that's the same as the right inverse for infinite dimensional things. So the unitary definition, usually it's this one, but it also implies the other one. All right, and that's where we left off. And now we're going to talk about projections. Any questions though about that short review? Okay, so projections. What's a projection? So projection has to do with having a subspace of your Hilbert space. So you have some H1 that's kind of a subset of your whole vector space. So you can imagine, like a set of vectors in here, and then we're looking at some portion of the space, which we call, H1. And this is also a Hilbert space. And that'll be important. And it just contains some subset of vectors. Typically, it's like one dimension less than your original Hilbert space. It's like, taking an XY plane and then looking, well, my light goes out after a while. And it's looking at a portion of it, right? So that's, the whole thing is H. So it's like projecting onto the x-axis, a two-dimensional plane. And then looking at vectors that just live along the x-axis. Those are also a vector space, right? Because you can just add and subtract vectors that live along the x-axis if you wanted. Okay, so then any vector in H, we can decompose it as a sum of a vector in H1 plus something else. And we're going to try to prove that this decomposition is unique, meaning that there's only one way to write it. And so phi2 is in everything, is a vector in everything. So let me so if the whole thing is H, right? The whole thing is H. Then H2 would be like everything outside of H1. This is like the complement. So this would be H2. So what we're gonna show is that any vector that lives in the entire H can be decomposed into two pieces, one which lives in H1 and one that is outside of H1. This is in this H2. And this is a unique way, meaning there's just one way. So we can actually just show that. It'll give us a way of showing how proofs of uniqueness work, how to show something is, can only be done one way. All right, so I'm going to clear this if that's okay. No. Or maybe I can forget if I can. Yeah, I can just do this. Okay, good. So we got projections. All right. So how do we? So we can prove the uniqueness. And the way we do it, we assume that there's some other decomposition. Phi is equal to phi 1 bar plus phi 2 bar. So we assume that there's some other decomposition, and all we just have to do is show that this decomposition is actually the same as the original one. That's how you prove uniqueness in general. But we know the following. We know that for any chi in our H1 subspace, what do we know? We know that we can dot chi into phi if we wanted. And what would that do? If chi is in H1, then by definition, since this is the part that's in H1 and this is the part that's outside of H1, everything else, then the dot product must only hit the thing that's in, phi, that's in H1. Whatever this other vector is, it's outside of H1, so the inner product with anything that's in H1 must be 0 by definition. So this must be equal to these two things. It just must be because the dot product with this guy or this guy, is 0. So this must be true. And so what does that mean? We can use now the property of linearity, right? Linearity tells us that then chi dotted into phi 1 dagger minus, or phi 1 bar minus phi 1 like that, that's equal to 0 for all chi in H1. And if that's the case, then the only possibility is that this vector, this is not possible unless this thing is just the null vector. So we conclude from that phi 1 bar is equal to phi 1. And of course, you can do that for the other component. You can look at any chi that's in H2. So that's it. That's the proof of it. We just showed that if you had some other combination, then you can't have that because what you really have is just the same combination again. Okay, so that's the.
A question. What did you mean by bar again? The
I just
bar?
mean this is how you prove uniqueness of something. You want to show that this is unique. So what you do is you assume you have some other way of decomposing it this way, where these are just some other vectors.
Okay, so that's the label just to denote that it's a different vector than phi1.
Yes, exactly. Just some other ones. And then what you want to show is that they're actually the same vector.
Okay.
And that's what we did. And the way we did that is we used what? The property of linearity, right? That, well, we used a couple of things. We first used a sort of definition of the projection of what a projection is. This is just the definition of a projection. And then we also used the fact that the inner product distributes over linear combinations. So we use this very key property of linearity, which means that, and then, you know, if this is true, if any vector, and then this is sort of the property of a Hilbert space, of a vector space, that if, you know, if any vector dotted into this guy is 0, no matter which one you choose, this is true for any, that the only possibility then is that either this thing is not in the Hilbert space, is like part of H2 or something, which would be a contradiction because we assumed that, you know, phi1 is in H1 and, you know, phi1 bar is in H1. So that's not possible. And so the only possibility is that this whole thing vanishes. And so then the two things have to be equal to each other. So the linearity and the whole property of a Hilbert space, the whole vector spaceness of it, gives you a lot of constraints. For instance, it gives you unique decomposition of your vector into a subspace, right? That's not obvious. Like, it's not obvious. You can imagine, you know, it's kind of like saying schematically, right? I have some subspace H1 and then like some other thing H2, and I'm saying that any vector that I take in here, like any vector, that I can always decompose it as a unique vector in H1 plus, you know, a unique vector in H2. And it's not obvious that that's, you know, unique, but it is unique because of the properties of vector spaces. It forces that decomposition to always be unique, so long as, you know, H1 is a proper vector space itself. And it's sort of intuitive, right? Like in real vector spaces, we can think about like a two-dimensional vector as being you first go along the x direction, then you go along the y direction. And there's a unique way of doing that, right? All right, so I'm going to clear this whole thing, I think. So that means we can now really properly define projection operators. Because we have this unique decomposition, we can define a projection operator onto a subspace. And this is usually written with this curly p. P1 acting on phi is just equal to, you know, phi1. And this is unique. It's a unique mapping because we know that the decomposition is unique. So again, it's a projection operator for some subspace of your Hilbert space. The little thing just means a subset or subspace. You can, and you'll show this on the homework. You can prove that, you know, P1 is Hermitian. And there's also a more obvious fact, and, you know, it's in the notes, but you also show it on the homework, so I won't go through the proof. But it's also should be pretty clear that if you apply P1 twice, right, that can't possibly do anything, right? Because if you apply P1 again to like phi1, that won't do anything because it's already in your subspace. So P1 squared is the same as applying P1 once. So that's a kind of defining feature of a projection operator. And you can also show, it can show that if some operator A satisfies A dagger A is equal to A, you can show that then A is a projection. That's another thing that's sometimes useful. Sometimes you want to prove that an operator is a projection operator, and you can, if you're able to show this, then you know it's a projection operator. Conversely, if A is a projection operator, then it'll satisfy this identity. So let's look at let's look at that a little bit and see why that might be the case. So suppose we'll just assume that A dagger A is equal to A, and then we can consider the set of vectors, you know, A phi. We can consider those set of vectors for all phi in your Hilbert space. And if it's a projection, well, then this set of vectors should form some kind of subspace, which we'll denote by H sub A, which it's like the set of all these vectors. If we take any vector in our total Hilbert space and we keep acting with it with A, then that should just project us into, you know, the subspace. So, and what would that mean? It would mean that we could take any phi in general, right, and decompose it in the following way. We can write a kind of funny thing. We can write it as A phi, and then we're gonna like add and subtract the same thing. This is kind of a funny thing we can do, but we can do this. A phi minus, phi minus A phi. This is just like seems like a very silly statement because what we're doing is adding, subtracting A phi. But if it's a projector, then, you know, this should really be, you know, morally equivalent to having, you know, like a phi 1 here, right? Or a phi A plus some phi 2 that's outside of it. And how do we know that it's like a proper subspace? Like, how do we know it? Well, we can check that this guy is orthogonal, right? Orthogonal to this guy. We can check that because we can just take A phi, right? And we can dot it into phi minus A phi. This is like checking that phi 1 dotted into phi 2, that's going to be equal 0, and we can just work it out, right? So let's work it out. We have A over here, so what do? Right, the usual trick, we can move it over using the Hermitian conjugate. So we get phi A and dagger phi minus A dagger A phi. We are going to use now, right, this identity, phi A dagger phi minus A phi. Now we have to do something else. We have to deal with this A dagger. Well, we can deal with it. We can use the same identity. A dagger is equal to what? Well, it's equal to A dagger A dagger. And this is something you will practice on the homework, and it's something worth thinking about is how you dagger a product of operators. And the thing that you do is you reverse their order. So you put the A over here and the A dagger over here, and then you dagger them again. So that's how you take a dagger of a product of things. You reverse the order, you flip these two things, and then you stick daggers in. And so you get A dagger again, and then A dagger dagger, the two daggers cancel. It's like taking a complex conjugate twice and then doing the transpose twice. So you get back out A, and lo and behold, that's the same as A. So that's, again, this another, indication here that we have a projection operator because it's Hermitian. So this whole thing is just phi dotted into a phi minus a phi, and by linearity, it's just 0. So that's 0. Done. Now shown that the decomposition, if you take any operator satisfying this condition, then this decomposition is a unique one, right? Or you decompose this thing into into two orthogonal vectors. So is this thing a subspace? Do we get a subspace where you have this decomposition to something in HA and something not in HA? That's what we proved, because we proved that this dot into that is 0. So indeed, this is in HA and this is not in HA, because these are orthogonal. So is it a subspace? Yes, and you can prove other properties of it. I mean, it should be. Other properties would be just like showing that this is a vector space, that linear combinations of vectors in here, are in this space also. That should make perfect sense because operators are linear. The operator is linear, so it distributes over linear combinations. So, any linear combination of these guys is also going to be in here. So it all sort of, you combine the properties of the linearity of the operator with the linearity of the Hilbert space, and you can just prove that it's a subspace. Here we just showed that the decomposition gives you two orthogonal things, orthogonal vectors. So any questions about that? This gives you a sort of flavor of how some proofs go, and also the mechanics of using daggers and things like that. It's important to keep in mind how that works. You'll prove some properties of these projection things on the homework, and you'll think, some more things to think about here. But any questions so far?
Yes, can you repeat the properties of a dagger, please? I don't know how you introduced, okay, in the last row
Yes.
of your screen. Yeah, can you repeat that again? Because it's not clear to me. Isn't a dagger A supposed to be the identity matrix?
No, so we're assuming a dagger A is equal to A. Now recall a unitary operator has U dagger U is equal to I. Yeah, it takes some practice. It takes some getting used to this kind of thing. Let me show some more things, I guess, then about it.
Yeah, thank you.
But all right, let's see if I can just do this sort of impromptu thing. Oops. So okay. So again, the main definition is that a dagger, you should be able to derive essentially all properties of the daggers by considering the definition. And so then things like suppose we had A, B, dagger. Suppose we had something like this, what we would do here. So using this definition, we would say, well, okay, then this must be A, B, right? This operator, whatever it is, chi, phi, that's definition. Then we can think, okay, so B chi is some vector. So this whole thing, this must be, B chi. And then I can just take this A and flip it back over if I wanted at the price of introducing a dagger, right? That's still by definition. And now we can think again, like, wait a second, this is just some vector, whatever it is, a dagger acting on phi. And this is a B, which we can pull over if we want at the price of introducing a dagger, right? So look at that. What have we shown? We've shown that, A, B dagger for any operators is the same as B dagger, A dagger, right? So yeah, there's some steps, but I assumed you sort of seen this before in undergrad, maybe not this formally. I don't know. You want to have any thoughts about this?
I guess it's just going to take, for those that don't remember the daggers, like you said, we just need to practice it because.
Yeah, take some practice. Take some practice.
Yeah, and I think it's also the way you're doing it because it's in symbology, like a dagger, you're not assigning like an actual, like, let's say a 3-vector, like 0, 0, 1 and 1, 0, 0 or something like that. For those that, because once you start practicing it that way, that's what helped me when I was studying, like you said, in undergrad, is I would assign it and you'll see these work out that way.
Yeah. I agree. So it'll take some practice. I guess for me, what helps me is just remembering always going back to the foundational definitions of things. This is the definition of a Hermitian conjugate. That's what we mean by saying we're taking the dagger of something. And I know it's tempting to go back right to the real space stuff and thinking about matrices, Yeah, it is tempting to go back to this kind of thing. But a lot of the, nice part about quantum mechanics is using this, so-called Dirac notation, where it is the same notation. It is the same thing as this stuff, in the end, but it's a little bit more of a compact way of doing things. But yeah, it takes some practice. So, all right. Any more questions? All right, so projections, there's some properties. We could just list some of these. You'll look at them on your homework. One property is if P and Q are projections, then PQ is a projection if and only if the P and Q commute. So if P and Q are projection operators, then their product is also a projection operator, provided that PQ is equal to QP. And the way you prove it is you can use that property that any operator that satisfies this is a projection operator. So you can you can start practicing with doing things like this, right? PQ. You have to show that this is equal to PQ, and at some point you'll have to use this property that PQ is equal to QP. That's the kind of thing you'll be doing on your homework. But you know, that's just something to keep in mind. Similarly, P plus Q is a projection if and the only if means that if, you know, if these commute, then it's a projection. If it's a projection, then it also commutes. So they're like equivalent things. You know, if you have two operators, then this is a projection. If and only if, that's what that phrase means, is that these two things are equivalent. PQ being a projection is the same as saying that PQ is equal to QP. The implication goes in both directions. And sometimes people write that as if with two F's, if and only if. And so P plus Q is a projection if and only if PQ is equal to 0. If that's just the null operator, just like multiplying by 0. And then also, you know, P and Q project into orthogonal spaces. And that's kind of worth thinking about, you know, the meaning of these properties. There is some intuitive meaning which you'll sort of think about for the homework. And of course, if you have PQ is equal to QP, then you can construct a projector like this, or Q plus P minus QP. That's also going to be a projector. And this projects onto the union. Is a projector onto the union of HQ and HP. So the way to think about it is, okay, you have some total big Hilbert space, then you have some subspace, and in principle, these spaces can overlap, and this is like HP. This is the set of vectors, you know, which P projects into. This is the set of vectors that Q projects into. And then, you know, all these different properties basically tell you different things about the subspaces that you can project into and what you can do as a combination. So for instance, this, provided that these two commute as in PQ is equal to QP, then this operator right here would project you into this space. The union. It would project you into this whole space right here. You can also construct something that projects you into the intersection of the two things. That would just be PQ, right? If PQ would, let me put this another color, PQ, right? That would sort of project you into the intersection right here, because first you would project into Q somewhere, and then you would project somewhere into P. So if you do that both, you know, if you do that, then you must be somewhere in this blue region. If alternatively you do this kind of thing, Q plus P, this is like projecting into both of these. This is like taking something that's in Q plus something that's in P, so it has to be in both. And then you subtract this off because you want to make sure you kind of don't double count the intersection. So, you know, this operator in red here, now it would project you into this whole space right here that kind of encompasses both of these spaces. So there's things like that where you can think about. It's not so important for us. It won't really come up very much. On the homework, you'll prove some of these things, and mostly the point of those proofs is just practicing your daggers and things like that, practicing using this kind of thing, and just maybe getting some sense of, projections. Again, this whole idea of if you have an operator A that satisfies this A dagger A is equal to A, then your Hilbert space is broken up into pieces. One is a subspace, a non-trivial fact, but there's a whole other Hilbert space generated by the action of A on all the vectors, generates stuff in here, makes its own little mini Hilbert space inside your big Hilbert space. And then you can, of course, have multiple, P's and Q's that do the same thing. And then you can ask, how does, if you introduce some other B, right, how does that space overlap or not overlap with the one that's generated by A. So that's the kind of intuition for these properties and what you'll be doing with them on the homework anyway. But it's not really so important for us in terms of like applying it to physics. It doesn't really come up all that often, like projecting onto the union of two different projective subspaces. It doesn't really come up that often. All right, any questions though about that?
Yeah, so you're saying that you have the A with some random vector, and that is going to be a subset of that Hilbert lambda. So it actually, so
There's
see where you
H.
have, yeah, so by the H, I don't know if that was,
It's an H. It's the script
mine
H.
is just like HA, and it was red. And so that new vector, okay, yeah. And then, but you said that one right there, that vector that you just created with double underline, that actually creates a subspace within the subspace, right?
No, so phi is any vector that's in your big
Yeah.
Hilbert space.
Yep.
And then if you take all of those and you act with them, you take A and act with them, this will form its own little subspace, H sub A.
Right, that's what I was thinking. So, and that's, but the
Provided, right, provided that A dagger A is equal to A.
okay,
Otherwise,
so
this
that's like
doesn't
a
work.
key, right? Oh,
Well,
right.
yeah,
So
because
that
then
has-
otherwise it's not a projector. A projector is a very special operator. It's an operator that generates a little mini Hilbert space inside your big Hilbert space, right?
see.
It's a
Okay.
different. It's like, for instance, well, no, I mean, it's a special kind of operator that satisfies this condition, right? In particular, it's like not unitary, right? For a unitary operator, you had U dagger U is equal to I. So the only kind of projector, which would be unitary, right, is one which, A is just equal to I, the identity. That's like, this is a projector, right? The identity is a projector because all it does is just projects you back into the whole entire space. And then, H A is just equal to H, if your projector is just the identity,
Yeah.
But yeah. Okay, any more questions? Let me clear this. So the last bit to sort of clean up with all this business before we move to like the serious proofs of quantum related properties is just this idea of Dirac notation, which we'll be using. We've been using it this whole time, but we're really now going to take seriously this idea that we can take this as a kind of dual vector to this guy, the ket. And what we're going to do is whenever we have operators and things like that, instead of talking about, the vector of, instead of talking about it this way, we're going to pull the operator out and just say that this is A. And we've already kind of done this. But we're just going to think about things this way. And then inner products, things that, we did that looked like this, we're going to write that instead as phi A chi like this. And this is all okay, provided that you kind of understand that when we write something like this, we're kind of implying that A is acting on the left, sorry, on the right here, that A is operating on this guy. See, it's unambiguous here. And this is, you know, this is what mathematicians would do. But we're gonna be a little fast and loose because we know that we can have A act on the over here, you know, using a dagger. We know how to flip A back and forth between these two by using the dagger operation for any operator. And so, and we know we have that Rice representation theorem that says that the set of these vectors is the same as the set of these guys. So we're just gonna always now use this kind of notation. Maybe I shouldn't say always, but you know, for the most part, we're gonna use this notation where you have some bras, you have some operators in here if you want, or maybe no operators, and then you have a ket like that. And that's like the same as this kind of inner product.
Hi, Max.
Yeah.
On the left here, where you say Dirac notation, and below that you have a bra and a cat.
Oh, yeah. Very good.
Okay, great. I didn't miss anything then.
I get these confused. The bra is the one that is like that. 'Cause it's the first one, and the last one is the ket, because then together they form a bra ket.
Got it.
Okay, so these are called bras, these are called kets. These are dual vectors, these are vectors. So you put operators between them, and when you have two of them, you get an inner product. You can get other things that are, you can write operators now in a different way. For instance, remember this decomposition that we had? You can, for instance, write the following. You can write chi as a decomposition into a vector phi, and then you take the inner product with phi and chi. That's like the component of chi along phi, right? And then you can add to it, just of course, you can take, it's the same thing as we did before with that projection, looking at the projection operator. You can add this and subtract the same quantity. Just rewriting the original vector can always do this. Right. And if we do it like, if we write it like this, then this is kind of, we can imagine this is like a phi 2, and this is like a phi 1. And what this is we can now reinterpret it using this Dirac notation. We don't have to think about this just as a complex number necessarily. We can group these things together. We can group these guys over here into one object, which is an operator. This is like phi. If we think about this as a single object, what does it do? Well, it would act on a ket, some kind of chi, right? And what would it do? It would spit out another ket, right? That's what the end result is another, it's a complex number multiplied by a ket, a vector. So it's another vector. So this object, it must take a vector to another vector. And so it's, by definition, you can show this is linear, and it's just an operator. So this is a kind of operator, and it's acting on some chi. And then the rest of it is just some, what is this thing? This is also some other vector. This must be whatever it is. I'm going to I'm just call it phi 2. So from here, we can define this projection operator as a projection onto a vector phi, and this is using this Dirac notation. It's a nice way of thinking about projecting onto a particular vector. in this case phi. And we can, of course, add them together if we wanted. We could take a whole set of them. We can write another projection operator. By the way, if you want to make sure that it's a projector, you can do this kind of thing. Let me show you how this works real fast in terms of the notation. So how would you do this? If you dagger this thing, the ket becomes the bra and the bra becomes the ket. It doesn't change anything. So you get phi, and then its Hermitian doesn't change. So basically, you know, if you take this kind of thing, daggered, the bras become kets, and you just reverse the two, but it's symmetric, so it doesn't change anything. It just becomes phi again. Again, you can go back to the original definition of what a dagger does and prove this if you wanted, but you know, it'd be a little bit too much at this point. But I just want to show you this. So then this is phi, right? Phi. And this thing, as long as, you know, phi dotted into phi is 1, you know, if this thing is equal to 1, then this thing is just phi, which is p phi. So it's a projection as long as you pick a normalized vector, one which dotted into itself is 1. So there you go. It's a projector. It projects onto the vector. It's like if you take two vectors, you can define an operator that just takes any vector and projects it onto some defined vector. It's like if you have an XY plane, you can choose any vector in there, and then you can project it onto any other vector. And then there's some operations, some matrix associated with that. And that's what this basically is. And so we can, of course, combine them. We can construct a sum, say, of a bunch of these projectors. And if, for instance, we choose our orthonormal basis for our Hilbert space, right? Suppose n is our basis for H. Then what? Then, of course, if we sum over all of these, what would this do? This would project, remember one of the properties of the projection, so this is where it does come up. One of the properties of the projection is if you sum up a bunch of projection operators, you're going to be projecting onto the sort of union defined by the projection onto all those individual subspaces. So if you pick a basis for your H, right, then each one will have its own little subspace, right? H1, H2, H3, and so on for your whole Hilbert space. And if it's a basis, then we know that any vector in H can be decomposed into a sum over the basis vectors. So if we sum over all of those projectors onto all those different components, well, we must just get back out, you know, the vector again in the Hilbert space. So this must just be equal to the identity. And that's called a completeness relation. So the identity is equal to, if we use the basis vectors for your Hilbert space up to the dimension of the Hilbert space, remember we had that, that's just, so this is a sort of key fact. It's called a completeness relation. So, and that's very useful in calculations, this kind of thing. And so this is where the Dirac notation really starts getting its power. Its calculational power is being able to write operators in terms of, you know, this kind of thing. A ket and a bra instead of a bra ket. in terms of these little projections onto vectors. And it's worth thinking about what this does in sort of, you know, in vector land, right? All you're doing is you're saying, well, let's do it in terms of vector. What is this even saying? It's just saying that, say you have like some vector, right, with x, y, z components, right? All this is saying is you take, and this is your vector v. All this is saying is, so what is the equivalent of like having x hat, right? This is kind of stupid, but what does this thing do? What it's saying is you take your vector, right, and you have along the x hat direction, what you do is you take x hat and you dot it into v, right? That's what this does. This is what this operator does. It spits back out something along the x hat direction, right? That's proportional to x hat dotted into your vector. That's what this bra thing does. It's the dual vector, so you like combine it with the vector. And this is just v1, you know, x hat, right? And now suppose we did it for all of the other components too, you know, the other basis vectors, y hat and z hat, right? What would these guys do? Well, they would add, you know, this would give us something along the y hat direction, v2, right? Because that would be the y component of v plus z hat, you know, v3. So in the end, when you do that, you know, when you take this operation of, you know, x plus y plus z, and you act with it on any vector, you just get back out the vector itself, right? Because you just picked out the individual components and pointed the vector along the little component vectors along those directions, and you just get back out the vector. So this is, and that's what this completeness relation means. It means, you know, any vector you can decompose into a basis, and that's what the completeness relation is talking about. It's just saying for each basis vector, you project your total vector onto that basis vector, and you add them all together. And it works because the basis vectors are orthonormal. So yeah, hopefully that makes some sense. Maybe, hopefully, at least with the, maybe you should sort of ignore this part because it's not really, I mean, we won't, this is just an analogy. So I'm going to put this whole thing in quotes. But hopefully with the analogy, it sort of makes sense to you what the completeness relation is even doing. But there's nothing mysterious about it. All that's happening is that we're defining a projection operator using a vector in our Hilbert space, using the Dirac notation. Allows you to define these projection operators, and then using the property of projectors, you know, it must be true that if you're using a basis and you're summing over all those projection operators, then this whole total thing must also be a projection operator, and it must in particular be equal to the identity. So it must project you back onto the entire Hilbert space. Hopefully that makes sense. And you can go back to those properties of projectors in order to like convince yourself that you know, that it's working. You can, you know, you can start doing things like proving properties, right? You can say you have your Pn and your Pm, right? And this would be M, and this would be N, right? You can start thinking about, you know, these things. Do these commute? So that's something you can think about for, and of course, yes, they do. Well, anyway, so any questions about that? You'll sort of see more of this on the homework, but the important thing to keep in mind is this completeness relation. That's important. Okay, so I'm going to clear this. Let me give you a little bit of an example of how you might use this kind of thing. Say you wanted to learn about the components, using some basis vectors, m and nth components of an operator, of a product of operators. Well, then let's use this Dirac notation, right? Very handy. You take the m, take your AB, and you take your n. That's what the matrix elements are. Then you can stick in a completeness relation. You sum over some p's, 1 to n. You can stick in a completeness relation right in the middle of these two things. If you wanted. And what is this? Well, this is nothing but A, it's the matrix, it's the MP matrix element, right, of A. And then this is the PN matrix element. So all you've done is you've just proven like how to multiply matrices together, right? This is just matrix multiplication, but written in this Dirac notation. But it's the proof of matrix, how matrix multiplication works. And I know it's kind of weird, right? You have to like change your intuition about like things like this and learn how to keep them together and split them apart. That's like the hard part of Dirac notation, is like sometimes you want to think about this as an object, right? And that's really the Dirac notation part, where you treat these as little projectors. And sometimes you want to treat them as separate and think about, this whole thing as, a little inner product. But, of course, they're the same thing. It's just how you group things. But that's what the Dirac notation lets you do, is it lets you recombine things however is convenient in order to, either prove something or show something, or calculate something. It lets you kind of mess around with the inner product and vector structure of your Hilbert space in this way, by again considering the real main thing is just being able to use this, right, as an object, being able to sort of multiply by 1 using this kind of object, the completeness. That's really the power of it, where it usually comes in. Other things, you can also, of course, have a trace of a matrix if you want, or a trace of an operator. That would just be summing over the diagonal elements of your matrix. So this is the trace. Any questions about that? These are just like little examples of how to use the Dirac notation a little bit and its connection to the actual matrix elements. Let's see if I want to say anything else. No, I guess not. That's all. That's all I want to say. Any questions though? Well, of course, we'll keep practicing all this stuff as we go along. Okay, so I'm going to clear this and go to the next main topic, which is spectral decomposition. This is really where all the physics, I guess, sits in some sense. So spectral decomposition, you can have any operator, A, right? Its spectral decomposition is, finding its eigenvalues and eigenvectors. And presumably you've seen this in linear algebra at some point, or in math methods. But in Dirac notation, it means what is that? So E for eigen, you find the set of vectors for which A acting on phi gives you back a number. And in general, this is some complex number times the vector itself. So it's kind of like, it's finding the set of vectors for which, this is true, that A acting on that vector, that set of vectors, gives you back some number times the vector itself. And, that's why it should be kind of intuitive why this is also called sometimes diagonalization. Because if you find such a set of vectors and they form a basis, then if you write your matrix in terms of matrix elements in this basis, then of course it'll be a diagonal matrix with the little numbers as the entries of on the diagonal, and everything else is just 0. So that's why it's called diagonalization. It's finding the set of vectors where if you write your matrix in terms of that basis of vectors, using that as a basis, where this would be like the 1, 1 entry for that eigenvector, the first eigenvector, and this will be the second one. Then if you write it that way, then you get a diagonal matrix. So it's also called diagonalization. And the way you solve, you just use the definition of it, the way you would find, say, the eigenvalues is you would just take A minus little a I. That's just rewriting this equation. Phi E, that has to be equal to, that has to give you 0 null vector. And so what you do is you can take the determinant. So that also means that if that's the case, then the determinant of this entire operator, A minus AI, that has to be equal to 0. And this gives you an equation to solve for this is the eigenvalue equation. You solve. So I talked about this during recitation a little bit. So how about if A is Hermitian? So this is where this idea of Hermitian really comes up. Remember, for us, it's A dagger is equal to A. If A is Hermitian, then imagine we take one of these eigenvalues, vectors, and we look at this inner product, right? So what would this be? This would be, by definition, A phi E, E for eigen, this is an eigenvalue, some number. But using this Dirac notation, right, we can also not only act on the left here, we can also use this to act on the right, because A is equal to its own dagger. So this is also equal to A phi, I'm sort of back to our regular notation, right? But it's also equal to this, because A is equal to its own dagger. And so then this, when we act with it here, now it's acting on the left here. And we have to use that anti-linearity thing. And now we will extract out an A star, right? Phi E. And so we conclude that A has to be equal to its own star, so A is real. So A is real. Very important. So Hermitian operators have real eigenvalues. And we'll see that that means that we can use these operators as measurements. And there's a little bit more. There's a deeper theorem, which will be related to being able to use the Hermitian any Hermitian operator to find a basis of vectors to use for your Hilbert space. So we'll get to that, I guess, next time. But here we are. So far, we've just shown that, you know, if A is Hermitian, then it has real eigenvalues. That's pretty good already. I guess I'll leave it off there. But any last questions about that? I would look at the recitation if you don't remember eigenvalues and eigenvectors. I'll talk about more about that tomorrow too. But I sort of assume you sort of already know eigenvalues, eigenvectors pretty well.